Welcome to our lecture online, and here's the introduction number 2 regarding simple harmonic motion. Now, in this case, we're going to look at simple harmonic motion in terms of time. And so the best way to look at it is here. We set up a similar system as before, where we have a mass on a spring. The spring has a spring constant K, the mass has mass M. At this point, it's in equilibrium, so the spring is neither elongated nor compressed. If we now pull on the spring and push the mass out at distance a, which then becomes the maximum displacement, which is the amplitude then of the oscillatory motion. If we now let go of the mass, then the mass will start oscillating back and forth with the spring. And so go from a maximum distance x equals a to maximum displacement x equals minus a, back and forth like that. We can liken that motion to the x coordinate of a phasor diagram here. For example, if we have something with the length of a, which corresponds to the amplitude of the oscillation, and we have that go around in a circle like this at a particular oscillation or particular angular velocity omega, we can then see that the distance x will always be the magnitude a times the cosine of this particular angle, theta. But then if we want to know how x changes as a function of its rotational motion, or how fast it oscillates back and forth, we can write it like this, that x equals a cosine of omega t plus the phase angle. Now the phase angle is only there if the object is not at this position when t is equal to 0. So if you think of the mass being at the end of this phasor diagram like that, going like this, and the x coordinate of this particular triangle being the distance away from the equilibrium point, then if that's the position, if position at x equal, or position at t equals 0, then this can go away. Then we don't need a phase angle. But if it's anywhere else at t equals 0, then of course we need to include the phase angle. So let's, for a moment, to make things simple, ignore the phase angle for now. So we can say that x is equal to a times the cosine of omega t. And notice that theta is equal to omega t. By definition, all right? Because we know that omega is equal to the delta theta delta t, and so therefore we can say that d theta equals omega times dt, and then say theta is equal to omega times t. And so that's what this comes from. All right, just a quick introduction of the relationship between the angle and the angular velocity. So now if we take the derivative of this, so if we now say what is the dx dt, then we take the derivative of the right side. This is a, and the derivative of the cosine is equal to the negative sign, so that's minus the sine of omega t times the derivative of the angle. And of course, since t is the variable, the derivative of that will be omega. So in other words, dx dt will be equal to this. And of course, dx dt by definition is the velocity of this object. So now we can say that the velocity as a function of time is equal to, let's see, we forgot the minus sign here, minus a omega times the sine of omega t. So here we have an equation that gives us x as a function of time. Here we have an equation that gives us velocity as a function of time. If we now take the derivative again, if we now say, well, dv dt is equal to, if we take the derivative of this, of course, that would be derivative of sine, which is the cosine. So we have minus a omega times the cosine of omega t times the derivative of the angle, which again is times omega. Or dv dt, of course, you know now that's the acceleration. So the acceleration as a function of time is equal to minus a omega squared, omega times the cosine of omega t. Now, of course, you also realize that the cosine of omega t times a is what we had over here, that's equal to x. So we can also say that the acceleration as a function of time is equal to a minus omega squared times a cosine omega t times a cosine omega t, which is equal to minus omega squared times x. So now you can see the relationship between the acceleration as a function of time and in the acceleration in terms of its position and how fast it's oscillating back and forth. But anyway, let me highlight this. So that's the third equation. We now have three equations. One describes position as a function of time, one describes velocity as a function of time, and one describes acceleration as a function of time. Now, what's this omega in here? It's also interesting to note that omega is equal to the square root of k over m. So omega is equal to the square root of k over m, or omega squared is equal to k over m. So if we replace these in here, so this can now be written as minus omega squared, which is k over m, times x. That is then again the equation that we found by setting the force equation of the spring equal to the F equals ma from Newton, and you can see the relationship between those two equations. All right, so now that we have our first set of equations that describe acceleration and velocity as a function of position, and the second set of equations that describes position, velocity, and acceleration as a function of time, we're now ready to do all kinds of example problems. So let's go ahead and get started on those.